our speaker is Anthony Kearsley. Tony, welcome. So as I do always, I asked him to send me a short bio, and he did. So the first thing he said is that he's a real Washington, D.C. native because he was born here, he was raised here, he went to school at the University of Maryland with his bachelor's degree in mathematics. And then, unfortunately, he left for his PhD. He went to Rice University, where he got a PhD in computational and applied mathematics. Over the years, he has worked as a faculty at the University of Massachusetts and at the Carnegie Mellon University. Now he works at NIST. That's where John met him. And he is a staff mathematician in the Division of Applied and Computational Mathematics. So he works at NIST. He collaborates with a lot of other scientists, with physicists, chemists, biologists, and engineers. Tony, welcome.
All right, well, thank you so much. And I want to apologize in advance. I am not very good at these internet presentations, but let's see what I can do. So I'm going to grab the screen. And then does that look?
Excellent.
And I can put this up. And then I'm hoping everybody can see that.
It's fine.
All right.
Fine for me.
All right, great. So the first thing I noticed when I brought this up is I'm not sure the title is quite right. It's Modeling Heat and Mass Transport in Cryobiology, but what I'd like to do today is sort of point at the sort of the notion of control and optimal control in addition to modeling heat and mass transport. So I've got three wonderful collaborators, Dan Anderson, who's a faculty member at George Mason University, but he also spends 1 day a week at NIST. He's a former NRC postdoc and has had a long history with NIST and has been a wonderful collaborator. James Benson is a former NRC postdoc who actually has jumped ship completely from mathematics and is now a faculty member in the Department of Biology after many years, but he's trained as a mathematician, and he's now at the University of Saskatchewan in Saskatoon, Canada. Danielle Brager, who just started with us, she's got fewer than 1,000 hours at NIST, but she's a current NRC postdoc, and part of what I'm going to point to at the end of this talk is going to be part of her work at NIST, and then me. So there's a nice theme here where we've all sort of passed through or are members of the Applied and Computational Math Division at NIST, Gaithersburg. So I also want to comment that when John invited me to give a talk, he said, "Oh, come down, you'll have a great time. We'll go to lunch." So I just want John to know that he's not off the hook and you still owe me lunch. So.
All right.
So, okay, so thought I would talk today about cryopreservation. So the motivation of this work is things like in vitro fertilization, where people are trying to freeze sperm or eggs or oocytes, and that's in fact the example we're going to use today. But the field is actually enormous. So this notion of banking or preserving biological tissue for long periods of time is just growing. There are cities that have enormous amounts of electricity usage because they power these huge refrigerators that bank biological tissues. So tissues, cells, cartilage, all sorts of medical, sort of medical applications, forensic applications, biology applications. For example, the Penn Smithsonian Cryo Initiative goes around and is freezing genetic information and genetic samples from endangered species. There's a movement to preserve genetic diversity among seed banks and things like that. So if a crop was particularly good, you freeze it and you keep a record. In 19 diggity do, this was a great crop, and here's what the weather was. This is the genetic breakdown of the seeds that had such a high yield. It's used a lot in forensic science. Certainly in the detection of volatile substances, and of course post-mortem analysis, but we're even getting trickier now. Things like cyanoacrylate, which is a fingerprint technique. They're even trying to pull off samples. So can I tell whether someone, for example, was using cocaine or something like that? So the freezing, the delicate freezing of biological tissue is sort of an enormous field. There's also non-biological applications. Things like gunpowder residues and things like that, which also require freezing to a very low temperature, but I won't talk about that. And finally, cryosurgery. So this is gaining in popularity quite a bit. So this is the idea where you freeze, for example, a tumor before you take it out. And there's strong, very loosely speaking, there's strong evidence that in many situations, especially some of these lung cancers, that if you freeze the cell, if you freeze the tumor first before taking it out, or before using radiation or chemotherapy, that this yields better sort of medicinal results. So so the sort of a lot of applications of cryobiology. Right, so just to sort of talk about length scales, cells are microns, 1 to 100 microns, maybe 200 microns, I guess, at the very top. I'll be talking about that regime. So an oocyte is probably the largest cell in the body. I guess maybe muscles, but it's up there. 1 micrometer, maybe 2 or 3 micrometers. Now you're talking about, okay, I'm sorry, no, that's wrong. So maybe 5 or 6 micrometers long and 1 micrometer tall, 2 micrometers tall. That's a red blood cell, which is also an enormous cryobiology application. So we're going to be in cells on the larger side, but people freeze tissue. Of course, the freezing of organs is an enormous enterprise, right? Harvesting of organs from for transplantation, and also cadaver freezing, which is the much larger scale. We're talking about 1 to 2 meters. It sounds kind of macabre, but in Dan Anderson's case, it would be 2 meters because he's that big. In my case, it's closer to 1 meter. So time scales, they're sort of flash freezing. So this is very, very fast. I'll say seconds. It could even be less, but let's say seconds. And then there's an enormous field of these controlled slow rate freezing. So these are machines that run, and it can run for 120 days. So very, very slow freezing. So you've got an enormous variation in the time scales. And for us, just between friends, we'll say our target is around minus 150 degrees for a target temperature. We'll call that cryo. People argue it has to be 160, no 140. I'm not going to do that, but let's call it around 150. That's the regime we're interested in. So the game here, the challenge here is the balancing act that we have to do. It is related to the fact that, roughly speaking, I don't know what happened. I just disappeared. Roughly speaking, ice formation in the cell when you freeze it means necrosis. That means death. So ice is to be avoided at all costs. The solution to this is, what I think of as antifreeze. So it's glycerol, ethyl glycol. These are called cryoprotectants, but they're antifreeze. The problem is, of course, they're toxic to the cell. So the balancing act is I want to slow the freezing as much as possible, but I want to do so in such a way that I use the minimum amount of essentially slowing mechanism as I can. So fast, I kill the cell by ice formation. Slowly, I kill it by dumping this antifreeze into it. So that's sort of the common theme to these development of protocols. So things like optimal cooling, optimal thawing or warming, and then preservation strategies. How do I maximize the likelihood that the biology of the cell is going to stay intact? So I'll touch on a couple of different objectives, but roughly speaking, it's ice nucleation, ice formation, and minimization of CPA. And the goal, of course, is survival rates, and I won't discuss it, but time and cost. If it takes me 280 years to freeze something, that's not going to help me. So today I want to talk about formulating a model for cooling a spherical cell. So this is an oocyte. So this is a real picture of an oocyte. This is what if you work in cryobiology, this is the cell that one would. There's a large desire to be able to freeze well oocytes and keep them intact. So I'm going to exploit the living daylights out of the spherical geometry here. I'm going to consider a thermal field. I'm going to consider a ternary aqueous solution. So these are these CPAs, these antifreeze, and then salt and water. That's going to be the three things I'm going to consider. And I'm going to have a solidification from the outside of the cell. So there's going to be a fluid. The cell's going to be in a fluid, and the fluid is going to be frozen, and it's going to creep towards the center of the cell. I'm going to assume, for the sake of this talk, no fluid flow and sort of dilute salt and CPA limits. Offline, of course, I'd be happy to talk about those, but that gets pretty involved if we don't make those assumptions. I'm going to formulate a couple of objective functions and just make some comments. This is just starting work, but this is going to be one of the focuses of Danielle's work is going to be moving these objective functions forward, and you'll see it's still raw. It's still we're just sort of scratching the surface on these things, and just talk about control issues, which again is sort of in its infancy. But down the road, and what Danielle is going to help me do, and Dan and I are working on now, is investigating more complex models. So non-dilute regimes we haven't looked at. When you add fluid flow into the problem, I have no idea. And then of course, more general geometries. So we just make a comment. So I think this is a fair model assumption here. I'm fairly certain nobody in the audience was the referee on the last paper we submitted, but the referee suggested, why not consider arbitrary geometries? I'll see you in 65 years. I mean, that's a very hard problem. So so we're going to stick with a very clean geometry here. So we've got a spherical cell at the center. We've got an aqueous ternary solution with the different radii. So you've got the cell, and then the cell comes out, and you hit RC. That's the radius of the cell, and then you've got this liquid, and that goes out to RI, and then you've got a solid on the outside, and the solid is going to creep forward, and these are all going to be time dependent. You've got a ring around the outside, and you can control the temperature along the outside. You've got a thermal compositional change inside the cell as it freezes, of course. You're going to have transport. The CPAs are going to move back and forth. The salts are going to move back and forth. And of course, you're going to have changing as a result of the freezing. So this is two coupled boundaries. So you've got this cell, this RI and RC, and these two things talk to each other. So it's a very complicated free boundary problem. I don't know why I can't move forward. So some of the modeling dynamics involve thermal diffusion in the solid and in the liquid and in the cell region. So the heat is going to move through here. You're going to have solutal diffusion. So these compounds are also going to swim back and forth, the CPAs, the salts, the water, the ice. And they're going to sort of change residence in between these three regions. You've got thermodynamics, which is something that we considered in our first paper many years ago, but that gets quite complicated. You've got the thermodynamics of this ice front separating these things going forward. From a ternary liquid, you've got the free boundary number 1, and then you've got this bio cell wall, cell membrane free boundary number 2, this semi-permeable membrane. We've got this external cooling strategy that I mentioned, spherical geometry, and I'll say a few words about our computational strategy. So for today, maybe that's too much, but I thought we could just talk about a simple problem. So this is modeling a much simpler free boundary problem. So just look at the numerical results will be on the previous problem, but for today, just talk about just simple thermal diffusion in the solid, thermodynamics of an ice front that's going to separate these things. So you've got one free boundary, and then you've got planar geometry. We'll just consider a thread. And for this, of course, we have an analytic solution. This is a classical problem from many years ago. So let's talk about that. So let's formulate that problem. So I'm going to start with this is our sort of starter problem. I'm going to start with just a general heat equation now. Rho is going to be the density of the solution. I've got a CP, which is a specific heat, and then I have another coefficient that sits in front of the temperature in the solid as a function of z. So z is going to be our string, our thread. Now we've got boundary conditions. So you have along the fixed solid boundary, you've got the temperature is going to equal the solid temperature, which is going to be the melting temperature, but a little more, so minus delta T. In the solid, it's going to be exactly equal to the melting temperature, and then you've got the latent heat and this chemical separation. So this is essentially the flux boundary condition that we have on the ice front. So so this is a classical problem. This is a Stefan problem. And for this problem, it is a large Stefan number. So think about the Stefan number simply being the ratio of sensitive heat to latent heat. Sensible heat is what the amount of heat, the amount of energy, the amount of heat required to pop you from one phase to another, liquid to solid or gas or whatever it may be. My thesis advisor was French and would always complain that we call this a Stefan problem, when in fact Lemay did it many years before. But anyway, we call it a Stefan problem. So in this case, if the Stefan problem is large, then I can take this TS solid term equal to 0. If I take that TS term equal to 0, I can simply solve for the speed of the solidification, and this becomes just a function of T. So this is our very pretty analytic solution to the much simplified problem. Okay, so getting back to our original problem, of course, this is much harder, right? So just a few words. Here you've got all sorts of thermal diffusion in all three of the regions. For a simple analytic problem, we don't have that. The solute diffusion with the three components, we're just going to ignore that. We ignore the thermodynamic. We only have one free boundary problem. We're not considering at all for the analytic solution. You don't consider at all the biotransport or anything like that. But you could still do external cooling and you've got even more than spherical geometry. You had just a line in that, and of course, there's no computational strategy required because you have an analytic solution to it. So let's just look at this in more detail. So on the outside of the cell, you want to keep track of of water, the amount of CPA, so that'll be one of the cryoprotectants that you've selected. You've got non-permeating salt, so you have a salt that you have to keep track of, and you're going to assume that outside the cell, the water plus the CPA plus the B, that's going to remain fixed. So you've got the temperature of the solid as a function of the radius and the time. You've got the amount of A in the solid as a function of radius and time, and you have the amount of B in the solid, the salt, as a function of R and T. Same thing in the liquid. You've got the temperature, the amount of A in the liquid, and the amount of B in the liquid. Both are going to be a function of R and T. Okay, so you move towards the cell, on the inside of the cell, you have the same thing. You've got water, but this time you have CPA, but in this case, you've got a non-permeating salt. So this is a salt that sits inside the cell but can't get out. So we have to keep track of that. So in this case, W, A, and C will remain fixed. And in the cell, we've got the temperature inside the cell as a function of R and T. We've got A, the amount of A, cryoprotectant A in the cell, and the amount of salt C in the cell. And now you have these interface positions. So now you want to glue these solutions together, and you glue them together at the, for example, at the solid liquid interface. So just a cartoon, just to repeat, you have these domains. You've got the C domain, the cell domain, and here the A will go between both the cell and the liquid and the solid. The C gets stuck inside the cell. It doesn't move out of the cell. The B will live inside the liquid and inside the solid, but doesn't go into the cell. And then, of course, water can live anywhere it wants to, so it passes between these things. And so we want to model these things as a function of time. All right, so let's go forward. So we use this is a standard diffusion equation for this, but I'm going to put it into polar coordinates because it's easier to deal with. So again, outside you've got the diffusion of heat, so that's temperature S. There's no diffusion of CPA and salt because these things are going to be frozen inside this block. In the liquid, you have diffusion of heat. You've got CPA and you've got the salt. And then inside the cell, of course, you've got diffusion of heat. This cell is going to heat up or freeze. And you've got CPA and salt moving around. And you have boundary conditions at these two R's, at these two capital R's, between the solid and the liquid and the cell membrane or cell wall, depending on what you're freezing. Okay, so a few more details here. So now you can talk about the full equation at Ri, capital Ri, and so this you're going to have here the latent heat times this. This is in this case it's a linear diffusion equation. You have the thermal conductivities. So this is the rate at which the heat moves through the medium. So the rate at which the heat moves through the solid or the liquid. The latent heat is a constant. It's the heat required to convert a solid into a liquid or a liquid into a vapor. You have these Ks, which are the coefficients. They're coefficients, segregation coefficients, which measure essentially the ratio of impurities that you have. You have solute diffusivities inside the liquid, and then you have this liquidus slopes. So these are, if you draw a function of a temperature where above the temperature above the graph it's in one state, and below that graph it's in another state. The liquidus slopes is just the rate of change. It's the derivative. It's the line tangent to that function at any given point. So I'm not making any references to other work, but I will talk about Conti's work in '91, who discussed a melting point of pure water, including these pressure-dependent effects, which is appropriate for our biological application. So that's what we used. Okay. So let me move forward. So you have a quasi-static approximation in the membrane. So if you look at the equation along this boundary or along the membrane, the change in the temperature between the liquid and the cell, normalized by the difference between these two, the distance, that's going to be that's essentially what's going to drive this process. So these heat flux conditions and this sort of gradient in the temperature is what's going to drive the freezing and drive the ice run. You've got exactly the same conditions, exactly the same differences that can be done for B and C. So it's essentially just matching the fluxes along the boundary. Let's just do one more of these. So gets a little more complicated for the thermal and solute balances. Here you have to include membrane segregation coefficients, and you've got coefficients that affect the permeability, how porous the cell wall or cell membrane is. But it's the same thing. You've got these flux balance equations that sit on top of every one of these boundaries that glue the solutions together. And it's these differences in the A, B, C, and temperature that drive the freezing, that move the freezing wall and shrink the liquid portion of the graph. So maybe just quickly say a few things, something about the membrane permeabilities. You have this conservation law here, so you can, if you look at the A in the cell minus A in the liquid plus C in the cell and B in the well, this is just the difference between the water in the liquid and the water in the cell. So you have these. You can exploit these conservations or these essentially a conservation. You've got these equality constraints where you add the different components in each one of the regions. So the differences in the CPA concentrations across the liquid cell boundary and the differences in the water concentration across the boundary, this is what I can say. It drives the mass transport, drives the temperature. The difference in the temperature drives the temperature, drives the A and the B across these membranes as well. Okay. So at time t equals 0, when we start our simulation, we're going to assume concentrations and temperatures are all uniform in space at time t equals 0. And then for early time t, if t is very small, there's a similarity solution for advancing the ice. So by that, I mean, I can gather the terms together and I can come up with a simplified analytic solution for that if t is very, very small. This is common practice. We do this a lot when we solve PDEs. We look for a similarity solution. So this is a kissing cousin of what was done in the classical Stefan problem. But ours accounts for this 3-component regime and has these added cryoprotectants and salts involved. The Stefan problem, which was initially to model freezing of the Earth, had much more friendly physical distances. There's nice healthy distances, and the medium was far more assumed to be far more homogeneous. So it was a simpler problem, but it's the same ideas follow. And so you can use this similarity solution and march it forward in time. So you use the similarity solution at time t equals t star, which is some you've moved in time, and then you just you use that essentially to march the time forward as a time stepping process. So I don't want to get too deeply in this, but there's a nice method of lines procedure that we developed, which is in our math biosciences paper, if you're interested. But fundamentally, we map these regions to fixed domains. So we normalize a coordinate x coordinate system for the cell, for the liquid, and for the solid. And if you map to this regime, you get essentially diffusion equations in each one of these variables. You can then discretize these and introduce fake points on the left and right of each one of these regimes, and build a nice method of lines, solution procedure. So we're only solving solving a set of ODEs with every time step that we march forward for each one of these. So it's a fairly robust numerical technique, and I think it's the best thing out there right now for solving these problems. Okay, so just point at some pictures of this. So here's a snapshot, and afterwards I'll try and show you a movie which I just put together actually a few minutes ago, but hopefully, knock on wood, it will work. But here you see some sort of fixed external temperature example. So you reduce the temperature and you see what happens. And here you can see you've got a black curve here that shows that you are getting undercooling. And by undercooling, I mean this is this desirable glassy characteristic to the cell. You want the cell to reduce below freezing temperature, but you don't want ice to form. So this is you can see that undercooling occurs here. So I picked a value where in fact the objective was met for this simple example. So this is t equals 0.5. I non-dimensionalized it for this. The distance from the center of the cell to the outside of the solid is 1, and everything's been normalized. But in normalized t equals 0.5, you can see the concentrations. This is a snapshot of the concentrations of A, B, and C, and the temperature. And then if you double it, you go to time t equals 1. You can see that the ice front is moving in towards the center of the cell, and you're beneath that local. The temperature is going to be beneath that local melting temperature. So that's good. That's very desirable. And the hope is that we'll be able to maximize that. Again, we model these things, so we march these things forward in time. And then t equals 4 this is now we're stopped. Everything is frozen. So everything is stopped, and there's no dynamics at all. We've just we've frozen. We've marched it forward, and we've frozen the cell, and this is where it sort of stopped moving. Okay, so you can see that the ice front grows inward. The cell radius is controlled by the fluxes of the CPA in the water. You won't be able to see much of a cell radius change, but you can see that the ice front, zoom towards the cell and then essentially freeze. And then this is the sort of the differential equation that we've integrated to get this. So for our optimal control, just for this talk, a simple, let's assume we've just got a linear external temperature with adjustable cooling rate. So we'll start with some T naught and T super naught, and then we'll have some gamma that modulates it in time modulates the temperature, so it cools it down. I like to imagine a wire that sits around this circular plate, and we can reduce that temperature through that little wire. All right, so this is our first attempt at this. This is really simple stuff. One of my great frustrations is that if you ask these cryobiologists what's sort of your dream cost function, if you ask 10 of them what their dream function is, you get 11 different answers. So everybody thinks that they know what the best sort of conditions are to optimize what the best objective function or cost function is. I don't think we know. Make another comment. With James Benson, he and I, when he was with me at NIST, we worked on just doing, at that time, people were really looking at just doing objective functions as a function of the cryoprotectants. So we're one of the first to get to the sort of the idea of allowing temperature dependence, I'm sorry, to enter into the optimal control, which I think is going to be necessary. So, all right. So the first one is sort of a min function that says these are these liquidus coefficients, but this is basically saying once you drop below a certain temperature, everything is the same. So this is a very simple proxy for undercooling. So if I simply remove the min function here, it's going to boil down to just trying to minimize temperature. But I know that's no good, because if I just try and do optimal control and minimize the temperature, bang, I've got ice in my cell and I've got necrosis. So this guy is going to turn off. It's not a very good formulation because it's non-smooth, but well, I mean, it's non-differentiable. But okay, it's a reasonable proxy for undercooling. And then this is just some sort of convex combination, or some not linear combination of essentially, well, let's just call it chemical exposure. This is just a proxy for the amount of antifreeze I'm subjecting my cell to. And so you can think of wanting to minimize both of those things. Okay. So I did not optimize at all. So there's no control. But what I did is I just took three values. So I took slow, medium, and large. Right. This is there was the story about the porridge. Right. So one is too hot, one is too cold, and one is, we hope, just right. But this is Danielle's job, is to find out what just right means. For now, we'll call it moderate cooling. So you can see you get enormous variation in the temperature at the cell center, and very different. Yeah, I mean, so they're clearly very different. This is A at the cell center. So you can see you get enormous change in A at the cell center as a function of how your cooling rate. This is C at the cell center. So same thing. You get a little bit of sort of, you can see strong nonlinearities here. The moderate flips with the slow cooling at the lower temperatures. And then this is the undercooling at the cell center, and again as a function of temperature. So there's no doubt that we've got a function. We've got a function we can optimize. I think what we end up doing will be probably close to these objective functions, but we're still playing with them. We're still not sure on what we will arrive. So this is just sort of summarizing what I said. For rapid cooling, you see partial solute rejection. So this is sort of the sieve, the cell wall is pushing things out larger than it should and faster than it should. So yeah, so complete solute rejection means that the solid phase is pure ice, which of course we don't want. Partial solute rejection means that salt from the liquid has bled into the solid. So non-trivial effect of partial solute rejection in the cell. Less CPA salt is present in the liquid. However, the ice front can move much faster with partial solute rejection. And so the exposure to chemical cell is larger. The way I like to think of this, and it's sort of simplistic, is that there's people who spread the cement and try and get the cement even, right? It's a function of how high the I don't know what you call it, the flat edge is above the cement when you spread it. Conclusions are we've formulated a spherical symmetric model for the cooling of this cell. We keep track of all these components in the cell, liquid and solid. Our model, I think, is incredibly appropriate for control issues. So we've essentially got the engine here. We've got all the means to keep track of all the things we need to in order to define a really nice objective function, a really nice control problem. And that's sort of on the to-do list. And then, of course, the real question are these, can we expand this? So fluid convection, I think, and fluid flow is going to be a big deal. That's very, very hard. Non-dilute models. I think if we try and perturb from the circle, if we try and get into non-circular, non-spherical shapes, I think the computational issues are going to be a mess. So if you look at something like blood platelets, they're really bad. I mean, they're about 2 or 3 micrometers thick. They're about 10, 8, 9, 10, I don't know, but about 10 micrometers long, and they've got this indentation in the center. So you've got a non-convex region. It's a nightmare. But that's something at least we can start to look at. Let me just go through the manuscript. So this is sort of our long list of papers. We've been working on this for a while. We started this in 2012 or something like that, and we were going to write a three-part series. The third part and final part was just published 6 years after the first part, which is about 8 or 9 years after we started. So there's a lesson here: don't do multi-part papers. And then the numerical work was done in this math biosciences paper. And then maybe I have a few minutes. Maybe I can just show a movie. I have no idea what these are going to look like, so just to show you, some go fast and some go slowly. So there's the little cell, and this is the cell center concentrations of A in the dotted line.
I don't see anything, Tony.
Uh-oh.
All I see is your references. You might need to close that.
So what do? I close this? I stop sharing?
Or shrink it, I don't know.
I have no idea. How about that?
Yes.
Yes?
I see a figure, yeah.
Okay, great. All right. How about now? Is it big?
Yeah.
Okay. So I have no idea. This may be a bust. No. Okay, great. So there you can see it freezing, right? Yeah, thank goodness. So there you can see it freezing, and it's funny, right? It takes a second to run, but actually it took a long time to compute this, so it's a little deceptive. But we can keep track of the temperature and the amount of A, B, and C, and the temperature going down. And then just for giggles, I don't know if I have to redo this each time. I did a bunch of different examples. So you probably, can you see this one? No. Is that one big?
Yes.
Okay, so that one's essentially the same. I had one where it happens more. This is sort of more, no, that one's nice and slow. One of them was fast, yeah. Yeah, so that's this one is sort of just guessing at parameters. This is what the flash freezing looks like, bang.
And I'm not seeing any animation on these later ones.
Okay, sorry about that. So let me see if I can't do that. What could possibly go wrong, right? Let's see, let me do this one. About that one. This one. Okay, can you see this one? This
This
was
is
the same.
cryo 1, cooling 1.
Yeah, so I'm just trying to find the one that goes fast. Kill these guys. Give me 1 second. Let me find the one that goes fast. How about that? Can you see that? No.
I glanced away and all of a sudden there was a new picture. Oh, there you go. Okay.
Okay, this is the flash freezing. So this one, you can see it happens almost instantaneously, right?
Yeah.
Bang, but you still get the changes in the concentration. So there's still sort of dynamics going on with the CPAs,
So
yeah.
the preservatives are still diffusing even though things are frozen?
Well, yeah, even though it looks mostly frozen, it's not completely frozen. So so if I go back to my analogy of the spreading the cement, I've spread the cement, but I've put it down very, very low, and so I've got this thing accumulating very quickly. So yeah, I'm still pushing it, you just can't see it very well, right? Because it's all accumulated, and it's slowed my pushing so much that it's still leaking back and forth, but you can't see it as much as when I raised my straight edge up and it was moving, and you saw a more uniform distribution as a function of time, right? So that's it. So that is all I had to say. I can stop sharing or put it back up.
Okay, thank you very much, Tony. Thank you.
My pleasure. So if anybody has any questions, I'd be happy to try and answer questions.
Well, I'll probably make you laugh. Going back to the referee's question about arbitrary geometries, it's probably going to be very difficult to do this numerically. Have you thought about trying to use random walks to look at this?
I mean, I've gone as far as to look at it,
Yeah.
but yeah, I mean, that certainly would be possible.
Yeah.
The only thing I've looked at, I've doodled on paper and looked at, if I think about my cell, my something like a red blood cell as being a perturbation of a circle, and then trying to deal with that correction to the solution as a random walk. That's the only thing I've started to look at, and it looks terribly difficult to me. It just looks terribly difficult.
Jack Douglas has done this stuff on hitting polymers with these random walks.
Right. I'm familiar with that. Yeah, he and Fern also did some other things on peculiar Poisson flow characteristics and stuff. So yeah, I mean, people have looked at these. I'm just terrified that the things are not going to cross off in a way, and I'm going to have a nightmare left on my hands. But I don't know. So I've only started to look at that, but that's certainly something I've looked at. Yeah.
Well, it just seems a way to approach a complex geometry.
Yeah.
But then in the different regions, you'd have different diffusion rates, so your random walks would be traveling at different rates.
Right, and
yes.
And the flux balance across the boundaries just terrifies me to no end. I mean, how do that just scares the living daylights out of me. I wouldn't know how to, and you've got stuff that doesn't go, at each membrane, you have stuff that doesn't pass through. So it's yeah, but it's certainly something we've dabbled with and looked at, but we haven't made any serious progress with it. Yeah.
I'm just curious. I don't.
Sure. No, and I appreciate the comment. But the big thing I think we're going to look at now is trying to come up with a more reasonable cost function. That's sort of our first, which sadly means talking with the biologists. But
Sadly.
Right. Well, yeah, right. But I think we're going to be able to get something a little better than what we've done.
Great. So, anybody else?
Okay, well, I think, thank you very much for your talk again. And, and if anybody else has questions later on, can I share your email?
Absolutely. I'd be
Okay.
overjoyed to answer any email questions or any comments or anything like that.
Okay, excellent.
Okay.
Okay, thank you.
Thank
All right.
you.
Thank you very much. Thank you.
And I do owe you a lunch, Tony.
Good. That's the most important thing. Thank you, John.
And thank you, Aleka.
Thank you. Bye.
Thank you, Aleka.
Bye.
Goodbye.
Bye.